So just before we get started, actually, I'm curious, how many in the audience have actually heard of Apache Calcite? Like, show of hands. Okay, cool. So a few. How many of you actually used it for something in production, or? Okay, definitely less people. Right, cool. Thanks. And so I'm Chris. I'm CTO and co-founder of Contiamo, based here in Berlin. Also an Apache Calcite committer. And Apache Calcite is really important for us at Contiamo. And I'm here to explain today why that is and what we use it for. So just a bit of background first of all. So Contiamo, our aim is to radically accelerate data access. And we do that by having a data catalog which centralizes both your data access and data governance. And on top of that, we support basically querying and building things on top of complex data landscapes with virtualization. Also providing materializations to actually make things fast in the end, because data virtualization is not always the fastest thing by itself. We provide connectors for lots of different database types. So, of course, relational databases, also object, document databases. Plus, we have lots of adapters for different data lake access. And so once you've connected your data to Contiamo, you can then modify, change the metadata inside of it, and query it basically as if it's a local catalog. So this is roughly how it looks. You probably won't be able to make those screenshots out too well, but basically provide a very nice user interface for all of this to allow you to query and visualize and look at data profiles. But we also provide lots of ways of integrating with visualization and exploratory tools out there. So maybe you're using Tableau or something else like this, a different tool. You can also connect that into our hub and view and visualize your data in basically any way that is suitable for yourself. So what am I going to talk about today? So first I'll give a very brief introduction to what is Apache Calcite, what can you use it for, what are the tools in it, and then after that I'm basically going to be talking about how we use this at Contiamo. So talking about basically Calcite as a toolbox of different things, different tools, which of those tools have been interesting for us and which ones we've used. Then talking a little bit about performance of our virtual layer on top of single data sources, and then moving on from single data sources to federated queries across multiple data sources across your entire landscape. And basically the problem there is trying to make this fast and efficient as well. So let's get started. So not too many of you, and so only a few of you have heard of Apache Calcite, but I'm sure if I asked how many people have heard of one of these projects here, the numbers would be much, much higher. Apache Calcite is actually provides some tools, some features which are heavily used by these tools here. So lots of Apache projects actually are using Apache Calcite under the hood. For example, it's used as the optimizer in Apache Hive. It's used as the parser inside Apache Drill. Apache Flink uses it for query optimization and query parsing. And of course, at Contiamo, we also use it for query optimization, query parsing, plus the things that I'm going to talk about in a second too. So, does anybody know what this is, what this represents? Any ideas? Anybody seen this before? No. So this is a deconstructed cappuccino, and the relationship to what I'm talking about here, Apache Calcite, is there was this great talk by Julian Ledem from flat files to deconstructed databases, where he basically talks about the concept that if you're building a database these days, you don't write everything from scratch. So you don't write your own SQL parser You probably don't want to write your own optimizer. Like, these things are a lot of work, right? So what you do is you take a piece from here and there. And a lot of those pieces, for example, parsing and optimizing that I just mentioned, plus data source connection and lots of other things, can actually come from Calcite. So you might write some super fast layer to pull the information you want from disk, from file system, but you don't then want to build your own SQL parser as well to actually give people a nice SQL interface to your product. So you can plug in something like Apache Calcite to help you out with this. So Apache Calcite, yeah, it's a pluggable framework. It's basically a collection of tools, of utilities that you can use however you like. So what does it have inside of the box? So as mentioned already, it's got a query parser in there. This is for standard SQL. So the standard SQL is kind of the default, but there are other ways of supporting a wider variety of dialects. Query rewriting. Materializations has kind of built-in materializations that it can even auto-generate in certain cases. A query optimizer, of course. It has a couple of different query optimizers inside of Calcite. One of them is rule-based, the other one is cost-based. It supports lots of different connections for all kinds of JDBC adapters and JDBC drivers and other adapters that may be for data sources that don't support SQL natively. Has an in-memory execution model, which basically allows you to do stuff in Calcite which the underlying databases might not support. Has support for SQL streams, and many, many more things. So let's take a look at a few of those in a little bit more detail, and I'll tell you basically these things we've basically used at Contiamo to really help us build this virtualization layer. So before I get into that, I just want to discuss a couple of things about terminology and architecture here. So there's a couple of sort of names in Calcite that you won't be familiar with, but they're fairly easily understandable. So a SQL node is basically what you get after you've parsed SQL. So you get some kind of tree, right? So a SQL tree. So it's called a SQL node inside of Calcite. The rel node is similar. This is basically your query plan, though. So you've gone from parsing your SQL to maybe a bunch of optimizations, but you basically end up with a query plan. And this is a rel node in Calcite. And then finally, there's this concept of a program, which can be one of the optimizers inside of Calcite. And you can, so either the rule-based one or the cost-based one, and you can combine those however you like, or you can just use one of them. Completely up to you. It's very flexible in the way that it allows you to put those all together. And on the left-hand side, you see this is the default way of using Calcite. So if you didn't plug anything else in there, if you don't configure anything too harshly, then this is basically what you get. So you start with SQL at the top, you go through your parser, you have a SQL node, then you go through this converter layer, and so then you basically start to build this logical plan, a logical rel node. Then you go through a bunch of optimization steps, which are completely configurable. You end up with a physical plan, and this physical plan you can then execute and get your data back with the help of what's called the rel runner here, which is just basically an executor. So now let's look at some of these tools. So we start off with the Babel parser. So the Babel parser is interesting. So by default, as said, the SQL parser accepts standard SQL, but the Babel parser basically extends that so it can support much more than standard SQL. It avoids making assumptions about certain keywords, so you can use date as a column name, for example, because some SQL dialects basically support this. It also handles like special syntax, like for example the Postgres double colon, which is used for casting. So, I mean, what can you use this for? So this is basically useful if you kind of want to impersonate a database server. You want to pretend that you're a Postgres server or an Oracle server. You can basically expose an interface that says, okay, we only accept Postgres SQL, but using the Babel parser quite easy to do this. Or I mean, maybe you have a client that's more familiar with one dialect than another. They don't want to use standard SQL. They want to use PostgreSQL again. Then you can basically enable this with the Babel parser. There are a couple of different rewriters in Calcite which allow you to basically rewrite these plans that you have. Internally in Calcite, it provides you can basically use the visitor pattern to do this, and we're transforming from one SQL node into another SQL node, or one rel node into another rel node. You can think of it just basically in terms of plan transformation in some way. So why would you want to do this? One use case would be view rewrites. So you can define a view. So selecting star from that view has a definition, and you basically would like to rewrite that to select star from the definition of the view. So you can actually do this inside of Calcite with these rewriters. And the same for row level security. It's a very similar use case, but row level security, it's used in it's available in quite a lot of databases. Allows you to say if you've got a sales table and you only want to give a specific user access to sales from Germany. So if they do a select star from sales, it will rewrite that to a select star from sales where the country is Germany. So, yeah, allows you to build these kind of things. And then we've got a plan builder, which is called the RelBuilder inside of Calcite. There are certain use cases where you want to go directly to a plan. You basically don't want to provide a SQL interface at all, perhaps, in your specific use case. So it replaces those top two stages with just a RelBuilder that goes directly into a logical plan. So this might be useful if your query is generated by some kind of model, some user interface that's doing a bunch of steps to get to defining a query, or you just want to avoid writing SQL by hand. You can basically use this builder to do something programmatically, which is then potentially type safe as well. So Calcite has a concept of statistics, which basically provide data, metadata about the underlying data source tables. By default, it has a statistics provider inside of Calcite, but by default, it also says that it assumes that the number of rows in every table is 100. So, if you want to get have a good optimization experience and generate a plan which is fast and efficient, you probably want to plug in your own statistics here to make this a little bit better. So this will definitely improve the cost and the weights kind of inside of the optimizer to get you a better plan. So it has materializations. You can define a materialization with SQL inside of Calcite, and then it will automatically rewrite queries that come in as they come in to use those materializations. And so a small example here, so let's say you have a page views table, which is very large. You've got columns in there, country and city. Generally, you might see a lot of queries coming in that are kind of saying, okay, group page views by country and by city. So let's materialize that. So basically tell Calcite, materialize page views by country and city. So it's basically a group by SQL query, right? We put that into a materialization called page views by location. Then query comes in. So we're selecting from page views. We're grouping by country and city, ordering by country, and getting the count for each of these combinations. Now, this can, of course, go down to the underlying table, to page views directly, but this is going to be kind of inefficient if you have to do this every time. So Calcite will see this query coming in, and then it will use these rewriters to say, okay, I have this materialization, I'll use that instead. And finally, the SQL dialects. So the SQL dialects are something inside of the rel runner, kind of inside of the execution model before the query hits the database. and it allows you to convert this kind of structure that you have into something specific for an underlying database. So let's say you're connected to a MySQL database. MySQL has a specific dialect that you want to try and hit. So you want to try and modify the query a little bit so that it looks right for MySQL, and MySQL will be able to execute that correctly. Inside of Calcite, they have a whole bunch of different dialects supported. I mean, of course, the main ones: Oracle, MySQL, Postgres, Hive, plus actually lots of others. And it's actually really easy to construct your own dialect and then plug it in. So you have a new database that's not supported in there. Then you can actually just create something like this. You just extend the SQL dialect. And what's really nice is that on this layer, you can also say things like whether it supports nested aggregations, whether it supports window functions. If it doesn't support window functions, then Calcite will see this and it will do those window functions in memory instead. So you don't have to implement everything in your underlying database. Lattices, I think I'm just going to skip here for now. So the conclusion. So there are lots of different tools. These are just the ones that we've really used a little bit in our company, but there's lots of other things inside of this Calcite toolbox that you can use. Really helpful to kind of build these complex applications. It's really very flexible, and they're all kind of pluggable, so you can choose which ones you want to plug in, which ones you want to use. Maybe you want to modify and tweak a couple of them. This is also possible. But you've really got to think about performance here. This is, if you plug all of these things in the wrong way, you could definitely have some issues there. So that leads us on nicely to looking at single data source performance. And so a couple of things before we actually look at some numbers, just to describe what we actually used here. So you've got to measure, right, when you're doing when you're kind of seeing whether you improve this performance or not. So what we used, and I would definitely recommend that, is some kind of standard SQL benchmarking tool. So TPC has a whole bunch of them. So exactly. So TPCH is the one that we used. We're also looking into TPC-DS. But TPC is just great for generating really kind of complex SQL queries that are difficult to optimize. So TPCH itself has 22 queries. It has a configurable data size. You can basically choose how big you want this data set to be, and then you can basically generate that for the data source that you want to test against. What's important here is that we're measuring the overhead here. So we're just looking at how much we add in our virtualization layer compared to running the query directly against the database. So things like the configuration of TPCH in terms of data size, plus the hardware that it's running on, is not the most important thing for us. The second thing that we found incredibly useful is tracing. So there is a kind of open tracing standard out there. There's a few different tools. Jaeger is one of them. It basically provides you with this. So for one single query, you can see how that's split up, where the time is taken. Is a lot of time taken in the parsing, or is it the optimization phase? You've really got to have some kind of insight there of what's going on. So this is really invaluable. And so I just want to. So we'll get into the numbers in a second, but just briefly mention query pushdown first, because it's kind of important to understand what that is. Probably a lot of you know what that is already, but just in case. So let's say we have a query. We're selecting from customers. We're doing some ordering there, and then we're just getting a limit. So if you convert this into a Calcite plan, it will look something like this. The best way to read these things, by the way, is to go bottom up. So start at the bottom. You're seeing that we're scanning on the tables. Then we're just, this is the select part of the statement, so we're just selecting the name and the ID. That's a project in relational algebra. There's this converter step here, which is not so important, but then you'll see that we're doing this sort on top, at the very top there, which right at the end of the sort, you'll see that the fetch is in there. So this is basically the limit, so the limit of 10. So this is a perfectly valid plan. This can be executed, and will give you the results that you expect. But you can see that the sort and the limit are in memory. So what this means in Calcite, you see this enumerable prefix here. This means that this is happening in memory in Calcite. The JDBC stuff, so it's clear that we're executing the query against the JDBC database. So if we can basically get all of the computation into the JDBC parts, then we're probably doing much better here. This is another plan. So semantically, this is identical. It's doing the same thing, except that now you'll see that the sort is a JDBC sort. And we would call this now a full query pushdown. So we've pushed down this sort and the limit into the database. And our aim is to avoid this case here, where we're doing lots of things in memory, because it means that we have to pull out a lot more. And this one is much better because we're relying on the kind of the speed, the performance, the optimizer of the underlying databases, which is good. So this is basically the test we're going to run here. We have some kind of runner, we have an underlying database, it's a relational database, and then we have our virtualization layer, the query engine. And we're basically going to compare these two runs for each of these 22 TPCH queries and see what the difference is. We're going to do 4 benchmarking runs in total. The first one, which is not, this is basically just to give us our baseline. This is to run directly against the database itself. The second one would be to run through the query engine, but just with the defaults that Calcite provides, so no custom logic there at all. The next one would be to run through the query engine, but this time adding some statistics. And then we'll go for something that's called a multi-phase optimizer that I'll explain a little bit later. And we'll basically compare these and see how they do. So let's start off with our baseline first. So you can see that the 22 TPCH queries running along the bottom. We've got time running along the top. So the lower the bars, the better, basically. The important thing to remember here is that, just look at the total time. So the total time in the top right here, 45.5 seconds. So if you just remember this number, then we can kind of see how that progresses over time. So this is our first run. So we basically go through unoptimized. So this is purely all the defaults in Calcite. So what it does is it generates some queries. It generates these 22 queries. And we can see that the total now is 158 seconds. So original being 45.5. We've added quite a bit of overhead here. Doesn't look too great. Yeah, that's true. Yeah, I'll actually come to that later. Yeah, thanks. So you see that this is very slow. What we look at, we look at the plans and we see how much push down there is. There's actually very little push down. There's actually a lot happening in memory here. And the planning step itself is actually consuming a lot of time. So, it goes through this planning phase before it even executes the query. That's taking up a significant amount of time of the query itself, which is obviously bad. So the next thing we're going to try is plug in some table statistics and see how this will improve matters. So plug in some table statistics here. So now we have basically accurate numbers for the row counts of each of the tables inside. And you can see, so comparing against the no optimization, you can see that now we're doing a little bit better in some cases. Some cases it's about the same, some cases even a little bit worse, but generally if you look over time, so the total 125, it's definitely come down. So it seems that we're going in the right direction here. Again, like a lot of the work is being done in memory, in this enumerable layer. The planning is still very slow. So this is one of the traces that we have here. You can see that the big bar at the top is basically the total query time, which in this case 11.1 seconds. And if you notice the second, third bar is the time that it's actually taking to do the planning and optimization. So that's like almost a third of the query, which is pretty bad for 11 seconds. To basically be in the planning phase for 3 seconds, this is not really what we want here. So the next thing is planning phases. So what do we mean by that? What we want to do is try and split up the planning into a couple of different steps. By default, what Calcite does is it just puts everything through the cost-based optimizer, which is less than ideal. We'll see why in a second. But what we want to do is now split this up into 2 phases that we'll call a logical and a physical phase. The logical phase we will run through the rule-based optimizer, which is called HEP in Calcite, and here we'll basically apply all of the logical optimization rules. So these steps can be performed without knowing anything about the underlying data sources. So, for example, it's always good to push a filter into a join, like these kind of rules. It's kind of always good to do them. So this would be our logical phase, and then the physical phase will actually use the cost-based optimizer again, and we'll apply all of these kind of the final physical rules and conversions that are needed to actually execute the query. And yeah, so now if we look at the numbers, we'll see that the green is the new planning phases compared to the old ones, so the previous best, which was table stats. And you can see like massive reduction in time now, so 59.5 seconds, which is a big improvement here. It's a bit more complex than that. You have to really set up and decide how you want the whole planning phases to go. So, yeah, exactly. So now, if we go back and we look, we now compare our final planning phases versus the original baseline. You see that some queries are slower here a little bit, but as somebody pointed out earlier. And in fact, it's even more valid in this case. There are actually quite a few cases where the query is faster now in the new planning phases than it was before. So generally, things are much faster. We've actually looked at the plans and we've analyzed the plans as well, and we found that actually everything is happening in those underlying databases. We're pushing down the full plan. The full query is happening underneath, which is great. Which of course means that it doesn't of course mean, but we've looked at the kind of serialization and the parsing and all of these other phases that we have in our layer, and they're really insignificant compared to the actual time the query is being spent in the underlying data source. So this is good. And as mentioned, some queries are faster than the baseline, and this actually surprised us quite a bit initially as well. But it's an interesting fact that basically the TPCH queries that start off, they go through this parsing and optimization phase. The queries that end up on the other end, that are finally executed against the database, can look very different from the initial queries. So, for example, there are cases where joins are turned into subselects and sometimes vice versa. So it's interesting that sometimes we come up with a query which is actually more optimal for that specific database than the original query. So, our goal for this was to do full query pushdown, because it's really difficult actually to even though we have full query pushdown, we can't kind of guarantee that we're going to be faster than just the raw query itself. We might be a little bit faster, we might be a little bit slower, depending on the query that we generate in the end. It's a little bit tricky to measure that. And it also depends very much on the optimizer of the underlying data sources as to whether we're going to be better or worse. So, but would recommend that, so if you're trying to do this, so that then the fastest way to get there, to get this full query pushed down, is to apply almost all of the rules into this rule-based optimizer first. That will give you a plan, which is a still logical plan because you haven't added any physical rules. But then you need to then apply this cost-based optimizer at the end to apply those physical rules and conversions. And then if you're going to use the cost-based optimizer, though, be careful adding too many rules. The cost-based optimizer works basically by finding a plan with the lowest cost. If you consider things like join reordering and different kinds of combinations of plans that you can have, that search space is just absolutely massive. So try and reduce the number of kind of the size of that space before you even start that optimizer. That's basically the rule there. And yeah, and overall just rely on the underlying optimizers to do the rest of the work to actually execute the query. So now let's look at federated query. So we looked at just single data source there. If we now moved on to federated query, so what is a federated query? It's a single query based on information from multiple data sources. So you have one SQL query. You could be joining a table from Hive, a table in Postgres, and getting some kind of result. Of course, this is going to be inefficient in quite a few cases. If you have a couple of very large tables, you want to try and join these in memory, then it's going to be difficult, right? Because that join actually has to happen in memory. There's no way we can now push down that join. You're joining from two different data sources. It's got to be done in memory. So got to be careful about that. If your driver has a large fetch size, so you basically, before you even start doing any kind of computation, you pull all of the data into memory first, and then start iterating through it. You've already kind of exploded your memory consumption there. This could also be a problem for single data sources as well. Any kind of aggregations, and basically anything that happens in memory, in this in-memory layer here. And when we get to, now that we're talking about federated queries, this could happen a lot more than for single data source queries, right? So in the best case, this will slow down your entire system. And in the worst case, probably things will just crash. So how can we solve this problem? So really the issue here is this in-memory layer that we have in Calcite. And there's a few ways that we can kind of scale that out. At Contiamo, what we've looked at is using Spark as the execution engine. So I'm sure everybody's heard of Spark at least. So it scales out to lots and lots of nodes. You can basically connect to a Spark cluster with dozens or more nodes in there. You can avoid OOM situations so you don't kind of run out of memory in most cases for Spark. And the other advantage with Spark is that it actually does have some Calcite support. As a bonus, Spark actually gives you a little bit better access to data lakes as well, so you can query things like Parquet files out of the box. I mentioned that it has Calcite supports Spark. There's a couple of different options available inside of Calcite itself. The first one is the Spark adapter inside of Calcite, and what this does is it takes this query plan that we have and turns it into a Spark plan. So it does a kind of direct translation. Then it has this plan, it sends this plan to the cluster, executes it, everything works. Unfortunately, we've had a little bit of a look into this, and there's still quite a few things missing in that translation. It's quite difficult to get right. The second option would be the Spark SQL dialect. We spoke about these dialects earlier that allow you to basically translate into the language of the underlying data source. So you could basically think of Spark as a data source almost, and translate SQL into Spark SQL. Unfortunately, this is we have quite a bit of overhead here because we're we're sending a query off to Spark, which then needs to be parsed by Spark. It needs to be optimized by Spark, which is not great since we've already done a lot of that work, and now we're having it done again. Plus the push downs in Spark are actually not as great as what you can do in Calcite. Calcite has a lot more kind of fine-grained control over that. The final option would be just to say, okay, then we just skip this entire Calcite layer and we just say that everybody just connects. Then we just have our customers connect directly to Spark, run Spark SQL queries. But then we were kind of missing all of these cool features from Calcite, this nice toolbox that we have. And again, the push downs in Spark are not as flexible as what we have in Calcite. So we decided to take another approach, and it combines a little bit of the ideas from these different integrations that exist already. So the first thing, of course, generate a Calcite plan. That's fair enough. Then the idea would be to identify the pieces inside of this plan, which relate to the separate data sources that we're actually connecting to. We would squash those individual pieces into what we call Spark tables. For every one of these Spark tables, those then become Spark data frames. And then the rest of the plan will just actually convert into, whatever's left will then convert into Spark SQL, which will then be executed in the cluster. So if you remember this architecture diagram earlier, it basically looks like this. So we're using all of these features of Calcite. Then right at the end, we have this physical plan that we then adjust and tweak a little bit, as mentioned here. And then the final thing gets executed in Spark and not in Calcite. So just to give an example of how that actually looks in practice here. So we want to join two different tables from different data sources. So let's say we have data source X, data source Y. So X contains our sales and Y is our customer data. We want to join those two, so the query would look something like this, right? So we're just joining those two tables using the customer ID, and we're adding a filter on the customer city saying that we're only interested in customers from Berlin. Then adding a limit here at the end just to get the first 10 results. So converting this into a Calcite plan. It looks a little bit long, but it's fairly readable. If again you go from bottom to top, you can see the two table scans there, one for customer, one for sales. And then the one for customer you see also has the filter on top for the city. And then those get joined together. You notice that the join is in memory, of course, because these are two different data sources. The only way to do that join is in memory. And then the limit is also in memory because it has to be on top of that final join. So let's apply our algorithm, our approach here. So we identify first the pieces from the separate data sources. So we've got this piece here first. This is from data source X, the sales table. And we convert this into a SQL query that can be executed on that data source. So selecting the customer ID, the sale ID from the sales table. We do the same for this other piece here. Gives us a slightly different query. We just basically have a where clause in there as well. And and then after we've done that, we can then take the Spark SQL dialect and transform the rest of the query into something that can be actually executed in Spark. So this is now how it looks after we've broken it down and converted these things into Spark tables. Well, those queries from the previous slide we've actually labeled as well, right? So you've got table 1, T1, T2 for those separate Spark tables, and now we basically have this Spark join and the Spark limit because this will actually be executed in Spark. So we've just done a straight translation from an enumerable join, which is a Calcite concept, into something that Spark would understand. And then we convert this final piece. We can also do this using Calcite, actually. We can convert this final piece into a query and then convert that query into the Spark SQL dialect. So that ends us up with very simple select star from T1, join T2, using the customer ID limit 10. And T1 and T2 are data frames at this point. And the nice thing is that in Spark, you can actually define these data frames with all of this push down that we've created, that we kind of have this knowledge of about what needs to be really pushed down and constructed in those data frames. So using this approach, we basically get the full scalability of Spark, along with the full push-down capabilities of Calcite. Plus, of course, we're able to keep this full Calcite toolbox that we wanted to use. We don't have any more bottlenecks through this in-memory layer, because we're now actually executing the queries directly on Spark. So we don't need to actually pull any data through that single node layer that we have in our virtualization layer anymore. And we can even use Spark to persist the results. So we can tell Spark to write this into an external database or into a Parquet file, however we like there. And the nice thing about this approach is that it's relatively generic as well. You could actually build one of these backends for a completely different query engine, execution engine, I should say. So I mean, Drill, Flink, Presto. We can certainly imagine that we might be able to use those instead and swap those out instead of Spark as well. So, yep, and that's it. Actually, if you'd like to follow me on Twitter, I put the slides up there later. Have a look at what Contiamo are doing on our website, and of course check out the Apache Calcite website as well, which has some nice documentation on all of this.
Right. Any questions?
What is the in-process overhead of Java processing in single data source?
Yeah, as I said, it's negligible. So of course it depends. If you're pulling out millions of rows, then you've got to be careful there. But generally, if you have full push down, you should just be able to pull out row by row, right? So you could have a fetch size, for example, in your database of 50 rows. So you pull out 50 rows, and since you're actually not doing any computation in that memory layer, there's actually not really much overhead because you're just pulling out the rows, basically. You're pulling out the result set. As long as you can push down the full query, you shouldn't have too many problems there.
Yeah, I wanted to go back to when you talked about the optimization that you did, where you separated out the planning phase from the I forget. Two phases.
The logical
right?
planning and the physical planning.
Exactly. Yeah, and so it seemed like magic. I don't really understand what happened there. Can you explain a little bit about why you got an improvement from doing that?
Yeah, one of the biggest reasons is that the cost-based optimizer you've just got to be careful with. Like you've got to know what you're doing. So the cost-based optimizer is basically state of the art. If you know what you're doing, you should definitely try and use that as much as possible. But if you don't know exactly what you're doing, it can take a lot of time to build a plan, which might not necessarily be the most optimal plan that you want in the end. So you've got to be careful. On the other hand, the rule-based optimizer, you can just give it tons and tons of rules, and it will just apply them and keep applying the rules until nothing changes anymore. So the only thing you've got to be careful there is cycles. So you could have a rule changing something, another rule changing it back, and then you go into some kind of infinite loop. But yeah, other than that.
Thanks.
Does Calcite has any support for UDFs, user-defined functions, and the like?
I believe it does, yeah. It does support UDFs. You can actually even construct them in Calcite itself and then use them inside of your queries. You can define a Java function which operates as a UDF, and then you can execute that in your queries. Of course, that will happen in memory, but yeah, it's possible.
Yeah, thanks for the nice presentation. You had to pull out some tricks to make this Spark Calcite execution running, as you said. Mm-hmm. Do you see an easy way or a reachable way for the community to kind of do this in Calcite so that others can use it more simply? As the Spark adapter was intended to be, I think.
Yeah, it's a good question. It's something we've definitely thought a lot about. Right now, it's really built into our application, and we've thought about ways of extracting that and to make it nice in Calcite. So we'll definitely continue thinking about that, and I would really like to actually push that back to the community if it's possible, for sure. Yeah.
Any other questions? Okay, so let's thank our speaker, please.